So once again, we want to say good evening to everybody and welcome to our webinar on the November 2022 Extreme Lake Effect Snows. I'm Joe Dele Carpini, the Science and Operations Officer at NWS Boston. And joining us tonight, we have a special guest all the way out from the forecast office in Buffalo, my counterpart, Dave Zaff, who is the Science and Operations Officer. He will be discussing this event with me tonight. And I just want to welcome Dave. He is actually a native New Englander. So Dave, if you want to just give a quick introduction and background about yourself, you're certainly welcome to do that.
Sure. Thanks, Joe. Hello, Boston. How are you? And as Joe said, I am from New England. Just a brief background about myself. Grew up outside of, we're in and around the Framingham area. My interest in weather started off with the blizzard of '78, and actually I guess they call it the Mother's Day storm of '77, and continued on my interest with snow off and on throughout high school and into college. I went to UMass, actually didn't do meteorology there, I did physics, and then I got a master's degree at the University of Arizona. And from there, I went right into the Weather Service. I've been working in the Eugene, Oregon office, the Salt Lake City forecast office, where I learned about lake effect, the Albany office, and now I'm here. I've been here in the Buffalo office for about 17 years. So I look forward to talking about lake effect.
All right. Thanks, Dave. And thanks again for joining us tonight. It's good to have someone who actually lived this event. I remember seeing a bunch of pictures that you shared, seeing a lot of snow. So welcome back to New England. You can never leave, as we always say. So I'm glad to have you aboard. And thanks so much for helping me present tonight. This is great having someone from the heart of this event. So we will get to you in a couple of minutes. What I'm going to do is start off is we're going to talk about lake effect snow, just give a basic overview, things like where it occurs, how it forms, and some of the forecasting tools, just a very brief overview. And if you want to learn more about lake effect and especially ocean effect snow that occurs here in southern New England, go ahead to our YouTube page. We did a webinar last year on it, including a review of one of our events. I believe it was in January. But that gives a little bit more of the detail as far as the processes and the forecasting of lake effect and ocean effect snow. They're actually very similar. And then Dave's going to take us through the event, take a look at the synoptic of the larger scale pattern that was in place, taking a look at some soundings, upper air soundings and some forecast soundings. That's one of the tools that we use. Performance of the high resolution models, the HREF, the high resolution ensemble forecast, that we rely heavily on in the Weather Service for our forecasting. And of course, some of the messaging that the Buffalo office provided, it really was very well forecast. And Dave, I remember you were notifying folks several days ahead of time this was going to be a big event. So hopefully that worked out for all your partners and the public, even though it was such an extreme event. So as Dave mentioned, lake effect and ocean effect snow actually occurs worldwide, not just in the Great Lakes, as you see here in the middle, but as Dave mentioned, the Great Salt Lake, it's pretty prevalent there. Another area is actually the Sea of Japan. That's a pretty well-known area for not lake effect, but kind of sea effect snow. Other areas include the North Sea and parts of Europe and the Black Sea out toward the Middle East. So it really occurs anywhere where cold air flows across an ocean or large body of water. And we've even observed lake effect snow off Lake Champlain in Vermont and also in the Finger Lakes in central New York. I remember my days in Binghamton, we would occasionally see little bands of Finger Lake effect snow, we used to call it, which would affect areas, say, like Ithaca, downwind of the lakes. So the process occurs when you have Arctic air traveling across a lake or a large body of water, picks up heat and moisture, and then becomes unstable. So the cloud and snow formation is enhanced by wind convergence and sometimes terrain convergence. That's especially true in areas east of the Great Lakes where you have, say, the Tug Hill Plateau east of Lake Ontario. And these are a couple of pictures I dug up from my alma mater, SUNY Oswego, but this was back in 1966. This was a pretty epic winter for lake effect snows in 1966. And I think, Dave, one of the years I was there in the late 1980s, we actually had our winter break. I left Oswego and there was about this much snow on the ground. I think it was about 4 feet. We got hammered for a few days. So certainly no stranger to lake effect snow in Oswego. So the lake effect process is convection. So think about the same process that thunderstorms develop under. You have instability, moisture, and lift. But we look at things like the wind consideration. So the direction of the wind determines the location of the snow bands, and quite often they can oscillate north or south as the wind direction changes by just a little bit. And then the amount of shear, meaning that the change of wind direction or wind speed with height versus the amount of instability, really tells us the type of bands that will form. So you can see in this example here, this would be an example of what's called frictional convergence. When you have the wind blowing across a lake, the frictional convergence or the wind convergence is always located along the southern shore. So think about it, this is either Lake Erie or Lake Ontario. You would have the convergence along the south shore of the lake and what's called divergence or more clearing across the northern part of the lake. So as I mentioned, lake effect snow is convection. You need the instability. So for that, we look at the temperature difference between the water and about the 850 millibar level, or about 5,000 feet. And typically look for about a difference of about 13 degrees Celsius. Obviously, you need moisture. It's needed for clouds and snow production. And then you need some source of lift. So there's a couple of ways you can get that. One is what's called larger scale lift, which is often what's called cyclonic flow, and Dave will get into a little bit of that from this event, but also the frictional and the wind convergence along the lakeshore. That helps as well, and sometimes even the terrain itself. Again, the Tug Hill Plateau is a pretty well-known area for getting lift and enhanced lake effect snow. So just to kind of show, when, obviously it's during the fall, winter, and spring, but why lake effect is more favorable then. If you look at the blue curve, that's showing us the lake temperatures throughout the year, and this is roughly over Lake Michigan. And you can see the water temperatures peak, late summer, like the ocean, after you have the strongest heating in June, July. There's a little bit of a lag as far as the lake temperature here. But as the temperatures start to cool as we get into the fall, this is September, October, and November. Notice now the lake temperature is warmer than the air. So that creates the instability that you need. And early in the season, it's often warm enough for lake effect rain showers. But as you get into especially November and December, January, February, that's when you're really primed for lake effect snow, assuming places like Lake Erie doesn't freeze over and you still have a moisture source. So as I mentioned, for the band types, the wind direction and the shear, so again, that's a change of wind direction or a little bit of wind speed with height, will determine the types of bands that form. So you have the larger single bands like there on the left. You have what are called multiple bands, which tend to produce lighter snowfall amounts than the single bands. And then you also have what's called cellular bands, which are more, we call it the spray gun, but that's typically what we see in ocean effect snow. You've just got a bunch of different cells, or think of them as like popcorn type showers or thunderstorms in the summertime. And it's really the wind fetch that, as I mentioned, determines the type of band. So the lower left here, we have an example for Lake Erie showing the maximum fetch is up about west-southwest, or from 250 degrees if you're using a compass, whereas a southwest wind is going to be somewhat less of a fetch across the lake and favor areas well to the north of Buffalo across Ontario. So some of the forecasting tools that are used, one is really pattern recognition, and that's something gained over the years working through these events. And we look for things in the larger scale pattern, like here on the left, what's called cyclonic flow aloft, which is kind of a dip in these contours that you're seeing. So that provides the cold air, provides a general source of lift across the region, and also the prevailing wind direction, where are the bands going to set up. So many offices have a forecast guide like you see here on the right. This is for Michigan, but you can see with the north-northwest flow, the areas that are highest risk in the lower areas of Michigan, the high risk, and even a very low risk at all. This is all based upon kind of the wind direction, and shows the fetch for each of those directions. So some of the challenges that we have, one of them is with the models. For example, our coarser models, think of things like the GFS model, for example. It's relatively coarse, and it struggles with some of the finer details like the band location, the intensity. It kind of broad brushes it. And you can see a kind of an old example here on the left. This is an old example of the NAM, just kind of showing a more blotchy features to the snow bands, whereas our higher resolution models, like shown here on the right, show a much more finely banded structure. They provide a lot more detail. So we rely really on the high resolution models of today. The NAM for one, the 3-kilometer version. As I mentioned, the HREF, which is an ensemble forecast of several high resolution models. these really can help pinpoint the areas. But even with those, a very small error in the wind direction can lead to errors in band location. So think about, maybe a 10-degree error in the wind direction could result in the band shifting 5-10 miles away, and resulting in a completely different outcome than what we expect in our forecast. So it's still very, very difficult to pinpoint these things. But the models of today are doing much, much better than even 5-10 years ago. So one of the tools that we use very heavily is called BuffKit, and it's widely available. If you do an online search, you can find it, download it, and even find all the data. But it essentially gives you the output forecast soundings from various models. And by doing this, we can identify a couple of things. For example, the depth of the mixing layer, which tells us the instability. So the deeper the mixing layer, the more more instability that you have available, so the more energy you have. And then the steering winds, as shown on the right, tells us the band location. We can assess things like the wind shear within the layer, and also the band location on the left tells you areas that are favorable. It kind of works like a traffic light: green with little shear, yellow with some directional shear, and then red with a lot of shear. But it's been around for a long time. It actually was developed at the forecast office in Buffalo back in the 1990s. So if you do an online search for that, you can certainly find it. It's free, and many university sites have the data available that you can download to look at different soundings. So we use it in the Boston office all the time for ocean effect snow in particular, but also for things like wind gusts and almost anything any part of the forecast, cloud heights, things like that. So very, very useful tool. And then if we look at soundings, this is a difference, comparing a sounding for a single band on the left versus a multiple band scenario on the right. So remember, our single bands are the big ones, like the one Dave is going to be talking about. But these single band events tend to have a higher inversion. So in other words, a deeper mixing layer. And this is kind of the height if you're going from the bottom to the top. So here's our inversion where the temperature starts to increase with height. So notice how deep it is compared to the sounding for multiple bands where it's quite a bit lower. And there's also a lot less shear, directional shear. Notice the winds here all from the west-southwest, whereas in the multiple band sounding, they're more out of the north-northwest, and there's a lot of difference in direction here in this mixing layer. So the single bands also feature the short parallel steering winds. That gives us that nice long band across the axis of the lake as opposed to being a little bit more perpendicular. So that's the general idea when you're talking about forecasting a single band versus a multiple band event. And often with ocean effect snow, remember, we have a very low inversion. So it's more the multiple band sounding. Tends to be a little bit more in the way of directional shear, but it's very, very low, even lower than this. So it's usually the lowest, about 2,000 feet that we're looking at for ocean effect snow, where in this case it can be 5, even 10,000 feet for lake effect. All right, so with that, that's a brief introduction. I'm going to hand it over to Dave, who's going to take us through this extreme lake effect snow event in western and north central New York. So Dave, I'll hand it over to you.
All right, thanks, Joe. I'm going to start by going right back to you and asking a question. You used a word and I couldn't think of what it was, couldn't remember what it was regarding the multi-band lake snow. What did you call it? What, like a spray bottle or something?
Oh, the spray gun. Yeah.
Spray gun. Yeah. Okay.
That's what we tend to call it. Yeah, we get that for our ocean effect snows, and I know it occurs with lake effect snow too.
So yeah. So for ocean effect and those multi-band lake effect events that occur downwind of, say, Lake Michigan and stuff, yeah, you could think of it as a spray bottle or spray gun. For the bands that occur east of Lake Erie and Lake Ontario, because of their orientation, they tend to be singular bands. And the analogy for the lake snow would be more like a fire hose. It's just incredible the amount of snow that falls out of these things. So sure, yeah, we got 6 feet of snow in the suburbs of Buffalo for this past event just a few weeks ago. Buffalo Airport was a little bit on the north side for the majority of the event, but they still recorded a 24-hour total of 21.5 inches. Makes it out to be, for what it's worth, again, just slightly north of the main event, their third snowiest in November. And it's something, these are types of events that, we really like to catch well ahead of time. And this was a fantastic forecast by our entire staff. We saw this a full week ahead of time. We started putting some messages out to our core partners, put it on social media to the public, and you'll see some of these examples of what we did. The strange thing about lake effect is we do have the ability, even though it can be several days out, we do have the ability to say that we're going to get a significant event in a very narrow area. And it's primarily due to the orientation of those lakes, Lake Erie and Lake Ontario. There's only so much directional space for those single bands to form. So why don't you go to the next slide? So here's our storm totals. They're unofficial because some of them are near record territory for 24-hour amounts. So we're actually doing a review of some of the reports that we got to see if they got any records. Locally in what's called Erie County, which is in Western New York, the record for a 24-hour snow total, I think, is 47.5 inches, and we were pretty close to that. I don't remember what it is east of Lake Ontario, but again, we're pretty close to record amounts and also close to a state record. So we're going over those numbers that people reported with a fine-tooth comb to make sure they weren't inflated or underreported in any way. But yeah, right now, those unofficial totals, 80 inches in Orchard Park, that happens to be the next town over from where I live. For reference, that's about 6 miles away from me, and I had about 50 inches. So just an incredible variation in the amount of snow in a very short distance. 73.7 in Hamburg and 61 in Watertown. Go ahead, Joe. Next slide. Here's a loop of what we call 500 millibars. That's about halfway up through the atmosphere. And you can see that very large trough that Joe had mentioned earlier. That's one of the things that we tend to look at. Another feature that's a little less apparent on this is actually if you go far west toward, say, Boise or into Portland, and you can see, you can see a fairly large ridge way over on the west coast of the country. And so that combination of an anomalous or very high or very large west coast ridge plus the trough over the Midwest and over the Great Lakes area, that's that combination that we typically look at for the potential for a lake effect event. We'll go to the next slide. Lower down in the atmosphere, this is 850 millibars or roughly 4,500 feet, 5,000 feet. You can still see that large trough over the Great Lakes. And what makes these events so fantastic is the persistent flow that you'll get along the entire fetch of Lake Erie and Lake Ontario. So you can imagine if you look at Lake Erie and Lake Ontario, they're kind of oriented from the west-southwest to the east-northeast. And that flow just sits over there for sometimes days at a time with very little movement. And it's those times when you're going to get these tremendous multi-feet events of snow. Go to the next slide. So Joe showed a sounding before. This is from the University of Wyoming, from an archive there. And what you can see here is the temperature on the right black line and the dew point on the left line. And then looking up of where the circle is basically right about where our inversion is. This is a summertime type pattern that occurs over the Great Lakes. And so what you're seeing here, as Joe mentioned, is you're seeing outright convection. You're seeing thunderstorms that just line up along Lake Erie or Lake Ontario and just move right up the lake and over to the Buffalo metro area and into the Watertown area. And this is also why we get thunder snow across area. Everyone gets so excited for the, once in it's like a lifetime event, you get thunder snow. You've seen the Jim Cantori, jumping up and down. It's really funny because we see that all the time here. So thunder snow is surprisingly not a big deal here, but it still sounds cool. But it's a convective environment. It's a small mini thunderstorm. The star shown here is representing roughly the lake temperature, and it's it depends on where you are on the lake. We're going to say it's about 11 degrees Celsius or about 51, 52, 53 degrees Fahrenheit. And in mid-November. The warmer the water, the more unstable this pattern is going to be. So you can kind of draw a straight line from that water temperature all the way up to where that circle is. And that shows you from this sounding standpoint how unstable it is. The sharper that curve is, or the sharper that angle, or the longer that angle, the more unstable you're going to get. The other thing that's highlighted here is that very nice wind field. There's not a lot of shear here. The winds go from very quickly to about 20 knots, 25 knots. That's the second. Yep, Joe's on the right, got it right there. And then it kind of hangs out there. It goes, you see the wind increasing a little bit to 30 to 40 knots, but overall, that's not a lot of shear. So it's a very low shear environment. That wind direction and wind speed is perfect for large dendrites, that classic six-pointed snowflake. And when those snowflakes fall one on top of each other, you end up with a lot of air in between, and you get a nice fluffy snowpack and high accumulation rates. Next slide. So here again is that buff kit tool that we tend to use. And as you work your way up here, you can see what we call the area under the curve. That's between the white line and the red line there. That's the convective available potential energy, or CAPE. And it's an implied value here because we're kind of estimating how much instability there might be, or potential energy. And the number here is shown as 1160 joules per kilogram. For reference, a decent thunderstorm is going to be about 1,000 joules per kilogram, and you get to 2,000. It's a good summer day. So we're pretty much in a summertime convective environment with 1,000 plus joules per kilogram. That's a good number. Looking at the wind barbs, or the wind, they're not really barbs here, but the wind on the right-hand side, again, you can see that somewhat sheared environment in terms of the wind speeds. But overall, 20, 25, 30 knots, not a lot of directional shear here. You can see the winds are steady all the way up through 700 millibars, generally out of the west-southwest. Next slide. Here's another sounding a little bit later in the event. You can see the CAPE is going to vary, and the wind direction is going to vary as well. For this event, the larger scale pattern, which we already showed, was persistent for almost 4 days. But embedded within that large scale flow, there were about 4 distinct shortwave troughs that moved through. And so for each one of those, the wind direction shifts just a little bit. So here's a situation where it shifted a little bit more. Where are we? On Saturday, okay. The wind had shifted a little bit from that initial direction that we were looking at before. You can see it's more of a westerly flow here. For what it's worth, this was right over my house. It was just dumping at this time. When you go to the next slide, you'll see that wind direction shift again. Notice on the right-hand side, the winds were out of the west-southwest. Now they're more out of a true southwest flow here. And correspondingly, if you look way over to the map, you can see that kind of 1990s course idea of where the lake band might be is actually north of Buffalo by this time. So the band, which was steady over what are called the Buffalo South towns for over 24 hours, it rapidly moved off to the north by this time. And you can see that the CAPE over Buffalo, convective available potential energy, drops from, remember we were looking at about 1,000 joules per kilogram, and now we're down to 742. On the next slide, now you can see, now we've moved forward to the point where the band has gone all the way north of Buffalo and has moved back south again. Again, there are a bunch of shortwave troughs moving through. So this was a time when the lake band was moving across the Buffalo metro area from north to south. And take a look at that CAPE, 1,200 joules, 1,246 joules per kilogram. The sounding is almost perfectly unstable. It's almost, you can't get much better than this. The wind shear, there's very little of it. The wind direction, wind speed, both of those are just everything is just perfect for this. on the next slide, what do we got? Joe, if you could go to the next slide.
Oh, did it not? You should be Sunday afternoon now. Are you seeing that one with the yellow?
Oh, I'm sorry. Yep,
There you go. Yeah.
I got it. So by Sunday afternoon, this is about the time when the band was really starting to fall apart. You can see that the Cape is dropping from what we were at 1200 before. We're down to 967 joules per kilogram. The flow has moved more of a west-southwest flow again. This is getting closer to the end of the event. Look how unimpressive. I'm not sure if I can come up with a better word. It just looks lackadaisical. What's the word I want? Unimpressive, I guess, compared to what we were looking at before with that sounding. Just doesn't look as impressive. So next slide.
Here, I can just loop back and forth. Let's see if that'll.
Yeah.
Let's see. No, it won't loop for me. Okay.
That's okay. All right, so getting on to the modeling, it's funny to talk about lake effect snow with Joe, because I remember being in Joe's office, I don't know, it must have been 2 or 3 years ago, and we were talking about trying to use the models to get a handle on, how much snow we're forecasting. I remember raising my hand and having this discussion with the other science and operations officers, saying, I hate to admit it, but we make it up. We make up how much snow is going to fall because the models can't handle it. All right, I got to backtrack off of that statement, because in this time, the models did such an amazing job. It was almost too good to be true. It was perfect. Now, in this case, it's a clear underestimation. The models only go for the snow up to 0.5. That's that dark blue, 0.5 inches per hour. And we know we are readily exceeding that value, or we are expected to exceed that value. So this is one of these cases where I could say, hey, we know better than this. This is just not going to cut it for us. And if this is all we had, we would certainly have to make up those snow amounts. But the HREF, or high resolution ensemble forecast, is a pretty amazing high resolution data set. It's 10 different model members, very high resolution, and they are able to capture the intense snow rates that we were expecting out of this. So if you go to the next slide, I think you'll see that. Here's an example on the max, in one case, at 8Z Friday, looking at the 1 hour mean or average snowfall, because this is an ensemble, so it's 10 different models all kind of blended in together, showing the snow rate of over 4 inches per hour, right over my house, really. East of Lake Ontario, a little bit later, there's one at 2Z on Saturday, the 19th. You can see those high snow rates of 4 inches per hour east of Lake Ontario on the right image as well. It's just fantastic. We've never been able to see models do this well. And this is an ensemble, so it's pretty impressive to be able to capture this. The location is fantastic. Oh, one more thing. So take a look at the width of these bands. For reference, if you were to go from the north part of one of these bands to the south part of one of these bands, that's equivalent to going from roughly Worcester to Boston. So maybe 30 miles, 35 miles or something like that at the most. And the rest of the area, it's dry with nothing happening. So kind of imagine, get into your mind what that might look like if you were to lay it on top of, say, the Boston area. It's a very narrow, intense lake effect band. Okay, QPF, or quantitative precipitation forecast. Kind of a esoteric term, but the HREF, or high resolution ensemble forecast, was forecasting over 4 inches of, essentially that's 4 inches of water. And that's hard to do in the summertime, let alone the winter. My house here, we had, I can't remember exactly, it was over 3 inches of liquid. So pretty impressive. Again, for the models to be able to forecast this is just fantastic. I'm thrilled to be able to see, finally, after years of, like I said, making it up, to be able to see the models actually do this. Next slide, please.
Dave, just a quick question on that. I mean, often lake effect is dry and powdery, and in this case, I mean, I think your ratios were what, probably 15 to 1 or greater. So even there was so much liquid, but there was also so much snow. Was this a pretty typical consistency that you had, or was it
Um,
heavier and wetter than usual?
yeah. So what's for frame of reference? The Boston area for your nor'easters, that's more like probably what, 8 to 10 to 1.
Yeah, anywhere like, 8 to 1 if it's heavy and wet, and maybe it's
Okay.
12 to 15 to 1 if it's powdery.
Okay. So let's say eight. We'll make it simple. A 10 to 1 snow ratio. If you get an inch of liquid, that would be 10 inches of snow. So what we were getting here was closer to about, like you said, about 16 to 1. So it's much fluffier than you get in the Boston area, which is sort of a concrete type of snow, hard to shovel, hard to move around. This was fluffier, but we typically get, especially as you move later on into the winter, into later December and into January, we typically get snow ratios of 20 to 1 or sometimes 25 to 1. We've seen 30 to 1, 40 to 1. We've seen some 50 to 1 snow ratios. It's almost like see-through snow. So 16 to 1 is that's actually our average over the course of any given winter. So it's not extremely wet for us, but certainly more fluffy than what you'd get out in the Boston area.
Right. Yeah. Okay. Yeah, that's what I kind of figured. But whenever I see 4 inches of water and, thinking Boston, I'm like, ooh, that's really wet. I'm like, well, not really when you have 50 inches. So,
Yeah,
so it wasn't too
the,
terrible.
the snow the snow is actually fantastic, fascinating because it accumulated rapidly and it settled rapidly as well. As soon as the sun came out, that 16 to 1 with those fluffy dendrites, the whole snowpack just collapsed by almost it's like about 8 inches for that first day. And then it was another 5 or 6 inches after that. So you can imagine these beautiful six-pointed dendrites just completely just disintegrating and turning into mush or ice or snow, or much granular snowpack. It changes very quickly. So you actually got to measure the snow quickly, or you're going to underestimate.
All right. Thanks, Dave. Appreciate it.
Okay, so this is just a continuation of that. And you can see, again, the model's forecasting 4+ inches of liquid, and that's what we were measuring. Pretty amazing. Okay, storm total, modeled storm total. You can see here those gray areas east of Lake Erie and Lake Ontario, getting up into that 30+ to 40+ inch range. I personally have never seen a model forecast 48 inches of snow, and we were almost laughing at it. We're like, I can't believe this is doing it, because that's what we were forecasting. Because I'll go right back to what I said before. We used to be making this stuff up, and here we are with an ensemble actually forecasting 4+ feet of snow. And people were looked at us like we were crazy, saying, you guys are forecasting 4 feet of snow. Are you sure about that? 5 feet of snow? But that's what we got. Next slide. Okay, we'll go on to the messaging part of this. So we were looking at this actually earlier in the week, over Friday into Saturday into Sunday. By Sunday, we were starting to get enough confidence to say, oh, my watch is talking to me. Excuse me. So as we got into Sunday, we had enough confidence to put some vague idea out that we were going to get a potential significant event. So that's exactly what we did. We put this graphic out, very rough circles or ovals in this case, to show for part of the event, we would think the lake band would be generally south of the Buffalo metro area through Wednesday night through Thursday, and similarly south of Watertown, east of Lake Ontario. And then having that band move off to the north, somewhere over the Buffalo metro area and somewhere over Watertown. Just a simple little oval to get the message started, saying, hey, there's a chance that we could get dumped on. As we got closer and closer to the event, it's a fairly complicated graphic here, but we started issuing watches, and the watches are all haphazardly, they're not haphazardly placed, but It's confusing because of the narrow bands themselves. As they start in one place, nothing's going on in another place. So you can't just issue a watch for all of Western New York. It just won't work. So the first band started the first watch was issued for the far southern part of Western New York, in this case, what's called Chautauqua and Cattaraugus counties. And then you could see we have that band starting later on in the Wednesday through Sunday for Southern Erie County, then moving off to Northern Erie County. If you look through, you can kind of see the start time if you read through all those words. So it looks pretty complicated. It was kind of complicated, but there's really no other way to do that because of those 30-mile wide band events. And 30 miles, by the way, is actually fairly wide for a lake band. It's not uncommon for our bands to be maxed out at about 15 miles wide. And at the beginning and end of some of our lesser events, some of them are pretty intense, but only 5 miles wide. So some of these events are just really hard to pin down. Next slide. So as we're moving on, let's see, we are now looking at, what day was this? Wednesday, I think that's Wednesday the 16th, I believe.
I think we had Thursday on this one, Thursday morning.
Was it Thursday morning? Oh, I see what we got here. So this is a forecast just for Thursday, And we are forecasting, this would be a big event. If you get a foot of snow, that's a big deal if you're out in Boston. So we're just getting the ball rolling here. You can see Buffalo, less than an inch. So a non-event for Buffalo, but south of Buffalo, it's a foot. Next slide. Okay, now I see how you got this set up. So by Thursday evening, the second of 4 shortwaves had moved through, and a band just started plastering the area. First moved well up into the Buffalo area, then settled a little bit further to the south. And you can see on this slide, we are talking about highways impacted. I put another image up here on the left, and you can see earlier in the day, they actually planned to close close highways to commercial traffic. Now, this is something we've been working with the New York Department of Transportation and some other local entities here, the New York State Thruway, which is kind of like the Mass Pike. Basically saying when we're forecasting 3+ inches of snow, your plows can't keep up. And what happens is as soon as one truck, it only takes one truck eventually will jackknife, and that's the end of the show. And people are stranded for hours, sometimes days. So we've seen this happen back in the 1990s, in the 2000s, and finally around 2009 or 10, we started talking with our core partners, the Department of Transportation, and like saying, hey, you guys got to do something about this. When we're forecasting 3+ inches of snow, you're going to get a major backup. And so starting, I think the first time we did this was in 2019. We were forecasting a major lake effect event, and they proactively closed the thruway. It was the first time they'd ever done it, and there were no backups. No one was stranded. It was a fantastic success, and people thought we were crazy, yelling at us, sending us nasty messages on Facebook and Instagram and everything else in between. And after that, people were saying thank you. And similarly for this one, people were like, "You're going to close the thruway? What are you nuts?" But there's a reason why that has to be done. We don't actually close the thruway. We just recommend that the DOT be pretty aggressive on what on their actions. So next slide. So Friday morning, so as we continue on into this, you can see, losing track a little bit of what's going on here because I think the dates are a little messed up, and my apologies because I told Joe one thing and I'm looking at it and it doesn't look right. Let's see, let me get my bearings straight here. Over Friday. Okay. So should have been by Friday, we were forecasting the lake band to be moving across the Buffalo metro area, still south of a good section of Buffalo, and then on into tonight. Look at the amounts. 8 to 12 inches, 8 to 12 inches. That's 2 feet of snow in a 24-hour period. You know, it doesn't look like a lot here, but it's not a storm total. These are just 12-hour totals. I'll go to the next slide. Here's another graphic later on to the evening. You can see we're still highlighting the thruway and some of the other I guess they're not interstates, but some of the other state routes and the interstate of 81 that goes north and south from Watertown all the way down, goes all the way down to Binghamton. On the left, you can see by this time there are already travel bans. So not just commercial traffic, but everybody stay off the roads. And I can verify this was a tremendous success. No doubt in my mind, we saved lives by having people stay off the roads. Those that did go on the roads and were driving around, there were people that got stuck on some of those secondary roads, but it was easier to get them out or dug out and get that road moving again by having the vast majority of the people stay off the roads. By this time, it was already pretty well apparent that you weren't really going to get very far if you go anywhere off of, if you want to go anywhere really. It was pretty much an impassable situation for the vast majority of any of the secondary roads. Move on, please, to the next slide. Okay, so here's just a few pictures. You can see a storm total in that smack dab center picture. This is Fort Drum near Watertown, that's east of Lake Ontario. Orchard Park just got buried. There are other pictures that probably might do more justice to this. It was just an incredible event. I mean, there were some pictures where you couldn't even see the cars. Just crazy stuff. Next slide. So as a summary, this is actually outside the forecast office here. You can see the airport tower off in the distance there. It was an extreme lake effect event. Oh, by the way, for these types of events, our staff, once they're in the office, they're not going anywhere. So some of the staff were there for, I think, 2 or 3 nights. And yeah, I call these sleeping bag events. How many days are you going to take your sleeping bag and bring how much food you want to bring? Because once you're there, you're not going anywhere. You can see for this event, it was a very well forecast event. We forecast 4 to 5 feet in the most hard hit areas. We got 4 to 6. The overall pattern was well recognized by our staff with that broad cyclonic flow, cold advection, steep lapse rates. You can see this a week out. The steering flow, persistent over the long fetch of both Lake Erie and Lake Ontario and not moving for days and days. And that warm water, relatively speaking, 11 degrees Celsius or 52, 53 degrees Fahrenheit, that provides that warm, relatively warm body of water that cools into the much colder atmosphere aloft, produces that instability that produces those large lake effect thunder snow events. Is that the last slide, Joe?
This is the last one here.
Okay.
Talking about the models.
Okay. Yep. Okay. Kudos to the real heroes here. It's the computer model program modelers, the ones that have made basically allow us to forecast the weather with any accuracy whatsoever. This new data set called the high resolution ensemble forecast, just phenomenal. It was unbelievable how well it did. The location, the totals, the snow rates, everything that was inside this forecast ensemble model was spot on. And that allowed us to produce spot on forecasts and very detailed, hey, you're in danger type messaging. Again, no doubt there were lives saved. In terms of fatalities, there were some fatalities. This was a very similar event to one that occurred back in 2014, where we got also about 70 to 80 inches of snow. There were 14 fatalities for that event. People were stranded for, again, days on the highway. In this particular event, there were, I don't know if there's an official number, there were some fatalities, mainly due to heart attacks from clearing snow. There were a few car-related fatalities as well. I'm not sure if those are factored in. But in general, as far as the highways go, nobody was stuck on the highways. So I will send it back to you, Joe, and I'll let you work with the questions, and I can answer any as necessary.
All right, great, Dave. Thank you so much. This was fantastic, and I really appreciate you joining us tonight, giving us kind of the inside look, because I could certainly present this, but you have obviously you lived through this event, so much appreciated bringing your perspective to us tonight and sharing your experience of this event. And I can remember too, Dave. Back when I was in Binghamton and we had lake effect, we would literally be drawing in the snow forecast because none of the models ever got it right. So it's good to see that they're at least a little better these days, if not fantastic. So very, very good. All right, so let's see. We'll go through some questions here, and Dave will probably end up answering most of them. But so let's see. So from Carrie, which bands are most likely to produce multiple episodes of Thunder Snow, the single or multiple? And I think you kind of answered that, Dave. Maybe just rehash that answer.
Yeah, generally the single bands are going to produce the Thunder Snow. You can get Thunder Snow from multi-banded events. It really depends on how much instability you have. There was an event that occurred here just last week where it was almost like a multi-band event, but it was thundering outside my window. So it's more how much instability can you get than single band versus multi-band.
Okay, and just following on that, is there an unofficial record of thunder snow occurrence to accumulations? And I think, Dave, other than it being in like a weather observation, I don't think there's a lot of records of thunder snow other than just, people letting us know.
Yeah, there aren't. Now, the one event that sticks out in my mind is a snowstorm that we call the October Surprise. It was in 2006 when we got, I think the Buffalo airport eventually measured 22.5 inches of snow. I might not have that number quite correct. It was close to 2 feet. And I believe for that event, we had thunder snow recorded almost every hour for 12 hours.
Wow. That's pretty impressive. I can remember some good storms in Oswego, and it was, like you said, the thunder snow happens almost all the time when you get one of these single bands. But yeah, it was a few hours of just, blue lightning and thunder. It was just incredible. So
Yeah.
definitely don't see it as much here as I used to see it in upstate New York, but that's okay. Okay.
Yeah.
Friend Jonathan wants to know, is this event, here we go, the usual question, Jonathan, that's okay. Is this event related to climate change?
Hi, Jonathan. So the standard answer I have to give is there's no individual storm that can be attributed to climate change. Now, if we were to start getting these every single year, then we might have something to talk about. But one event does not really make, especially something that's very localized for these lake effect events, really can't attribute a single event to climate change. And for what it's worth, we've had these events in November for decades. I mentioned one in 2014. I mentioned that one in October of 2006. That was a pretty big event. We've seen these going back through our records, going back to the 1970s, the 1950s. We have events going back into the early 1900s where they were talking about the issues with livestock, and not even talking about the electric grid because there really wasn't one back then. So, overall, we know that the climate is changing, but this particular event, you can't really tie it down to it.
Yeah, I agree, Dave. And, you could make some argument that, the lake temperature is warmer a little bit, later into the year, possibly, but that's probably more something for the climatologist to take a look at, as opposed to a single type of event. So this event, Jonathan, could become more likely with climate change because of warmer lake temps, but that's something that's just going to have to be, looked at over a longer period of time to kind of determine that. But good question. And it's one we frequently get that one, Dave. I guess you guys do too. So it's certainly part of changing climate, more extreme weather. Okay, from Sebastian, he said, we mentioned the high snow to liquid ratios in the Buffalo South towns and how if we didn't measure frequently, compaction would likely occur and lead to underestimated totals. So he wants to know, I know some people measure snow totals every 6 hours. Some people just measure a total at the end of the event. Do you think this difference in how totals are reported would lead to an inconsistent post-analysis snowfall map due to the magnitude of the event in combination with these high snow-to-liquid ratios and kind of ease of compaction? So that's a good question. That's one we deal with all the time, Dave. I don't know
Yeah.
if you saw that.
Yeah, the answer is probably. The issue, the idea, there's actually a fairly rigid set of instructions on how to measure snow. The Weather Service has documentation on how to do this. So here's what you're supposed to do. You're supposed to have a snowboard. It's supposed to be, what is it, 2 feet by 2 feet, it has to be white. And you're supposed to measure the snow, assuming it's snowing continuously every 6 hours on that snowboard, dust it off, bring it up to the top, and continuing that at 6-hour increments. You measure more, you're going to overestimate. You measure less than every 6 hours, you have the potential to underestimate. Now, in all reality, most people aren't going to get up in the middle of the night and measure snow. So there's the potential for underestimation. Then there are people, we know it happens, who measure every hour. So they end up overestimating. Now there's a whole nother issue here where, you know, you have some places that are, where you might have some wind drifts in one location. Just looking at this one picture, you can kind of see it's not a steady flat amount of snow here. So if you were to measure between the two, the car and the picnic table here, you're going to get an overestimation, where if you measure somewhere else, you might get an underestimation. So the best thing to do in this case is to basically take a lot of reports from a lot of people. And hopefully we've done a good amount of training for our trained spotters, such that they're measuring appropriately. We do the best we can. I suffer, you know, right out my window. It's tough to measure snow. It's that 6-hour idea, getting good estimation and average across your lawn, making sure you're not getting in a drift. It's hard. So it's really all about good education and getting a lot of reasonable reports. We know some are going to be overestimated, some are underestimated.
Right. Yeah, and you know, we see the same thing with snowstorms too. Just tell people, do the best you can, and you know, just try and educate as to the kind of the proper way of measurement. But it's never easy, especially when the wind is involved too. All right, let's see. Next question from Bill. How much snow is on the ground today where they reported the deepest snow locations? Is there anything even left, like east of Tug Hill and the south towns there?
Bill, there is no snow on the ground.
Gone.
It all melted. It melted in a week.
Wow, pretty quick.
Yeah, it's crazy. And we've had the same scenario back in 2014. We were actually worried about possible flooding from how much snow we were going to get. And this time we weren't really worried about it at all. How much snow we were going to melt, excuse me. This time we weren't really worried about it at all. We had a couple flood advisories, or excuse me, flood warnings that we issued for some of our rivers, but overall, it's surprising how quickly it can melt. And a lot of it compacts, remember, we were already talking about that. And so the idea of 50 inches of snow or 80 inches of snow, before you blink in it, and it's half that size. So it's not a big of deal as you might expect. The one issue that we have with it is not necessarily how fast it's going to melt, but how much snow is on flat roofs. And that's a problem. We lose garages, older buildings that are a little less structurally sound. We have seen a number of incidents with greenhouses in particular. They're no match for 80 inches of snow. So that's a bigger problem than having it stick around for a long time. Okay.
Interesting. Yeah, I remember it melted fairly rapidly. I was looking at some of the reports. That was pretty impressive. Let's see. Jonathan's got a good question. He's our snow guy. So how does this event compare to the historic event from January 1976? Do you remember that, Dave? Were there any comparisons?
Okay. My guess is you're referring to an event in 1977. During that event, that's known as the Blizzard of '77 for the Buffalo metro area. What happened for that, I won't go into too much detail, but that was one of the coldest years on record across the country. There's some fantastic stories about what happened leading up to that event. And what we had was basically a blowing snow event. The lake itself was covered with ice. Not only was it already covered with ice, but it was covered with about 3 feet of snow. So basically, all that snow just kind of blew around, blew over the Buffalo metro area and caused tremendous drifts. From what we were able to measure back then, we estimated about 12 inches of snow. The rest were due to drifting. The rest of the event was due to drifting snow. It was a multi-day blizzard. So it's what you could call it a lake effect event, but it was really more of a multi-day sustained not high wind event, but multi-day blowing snow event for the Buffalo metro area. And it was highly localized downwind of Lake Erie.
Yeah, and Jonathan's in 1977, so yeah, that's correct.
Okay. Good.
Wow. Yeah, that was one of the, I know the other historic one was the 66 one that I mentioned earlier, but 77 was the other one that I always heard about out there. Great. Let's see, John wants to know, would lake effect snow off Lake Champlain tend to occur oriented off the long axis of the lake? And Dave, I believe that's correct. More of a northerly flow. I'm trying to remember. I don't see it. It doesn't occur that often, but typically, yeah, it will be on the long axis of the lake. I know it is for the Finger Lakes.
Yeah, and with Buffalo or with Lake Erie and Lake Ontario, you can get a reverse lake effect as well. So you can get a lake effect that goes from west to east off of Lake Ontario, for example, and hits Toronto. It's pretty unusual, but it does happen. Yeah,
and we see that with ocean effects sometimes too. When we have a very, very cold air mass over us, and the highs moving offshore, we get into southwest flow. We can get a big single band south of Martha's Vineyard and hit Nantucket from the southwest. Yep. So we see that reverse sometimes too, when you get the really, really cold air masses over us and the highs starting to move offshore. So that's kind of the reverse ocean effect that we get as well. So
right, and yeah, for Lake Champlain, you can get the lake effect band, but they're going to be pretty narrow.
Yep. Okay, let's see. A couple more questions, and then we'll get on to our weather briefing. Ferris wants to know, how can I be a trained spotter and provide reports to you guys? I know for our office, and it's probably the same with Buffalo, we have spotter training. It's typically in the spring for severe weather, but that's pretty much when we also cover some winter weather reporting too. So I know you're local to us, so you can check our webpage. Usually we put the announcements out in March, April timeframe, and do our training in the spring. And I think at Buffalo, you guys probably do a similar program, Dave.
Yeah, so we do a spring program just like the Boston office, and we also do a winter program as well because of the interest in snow.
There you go. All right, but yeah, and you can report anytime on like social media. Just tag us on Twitter or post on Facebook, and we'll see those reports as well. Or even on our homepage, there's one of the icons near the bottom is send us your report, and you can just feel free to send us your reports. You don't have to necessarily be a trained spotter. It's good just so you know what to report and kind of how to report. But feel free, especially with snowfall. Everyone has a ruler. Just send us your reports. You're certainly welcome. And let's see, a couple more questions here. They're still coming in. Couple of ones to finish. From Elizabeth, how cold does the lake water need to get before the lake events start to slow down?
Okay. Before I answer that question, I just want to just completely do a quick shout out to say my mom is on the line. Hi, Mom. How you doing? Now I'll go ahead and answer the question. So the lake temperature will typically cool, of course, to about 32 degrees Fahrenheit. And then it will start to, at least Lake Erie will tend to start to freeze. Once you cover that lake, the party's over generally. You really need that, that transfer of heat to produce that lake effect event. And you do need some moisture as well. So there's a rough rule of thumb. We were looking at what was called 850 millibar heights before on the slide. One of the things we look at is 850 millibar temperature. And a general rule of thumb, it's pretty simple. You would need about 13-degree difference between the water temperature and the air temperature at 850 millibars, or about 4,500 feet or so. that creates a steep enough lapse rate to produce that instability that we're looking for. So as the water temperature drops from, let's say, the 60s to the 50s, 40s, and all the way down to 32 degrees, if you can get that air mass aloft, it's, let's say, at 850 or 4,500 feet, if you can get that difference between the water temperature and the air aloft to be more than 13 degrees Celsius, game on. But once that water freezes, at least for Lake Erie, it pretty much turns off the lake effect event.
All right.
Good question.
And yeah, Lake Ontario, I don't think it's ever frozen over, but you get some ice near the shore, but
Yep.
that typically goes through the whole winter. And Dave, Mom says hi back in the chats. So, okay, one more question, and this is a good one too from Bill. Is the reservoir in Western Mass large enough to get lake effect snow? That'd be the Quabbin Reservoir. And actually, we have seen some flurries off of it a few times. You're not going to get bands of snow that's going to pile up, but we have seen occasions where it's been cold enough and enough of like a northerly flow where we've seen some flurries off of it. So and even some clouds. So not quite big enough to get the snow bands, but yeah, flurries certainly. So it can occur in some cases if the air is coming across as cold enough. So it's a good question from Bill to wrap it up. So Dave, that's all I see right now. So I want to thank everyone for your questions. And Dave, again, thank you for joining us tonight. This was great. Love having you give us your perspective of this event since, again, you lived through it. And I don't think you were stuck at the office, right? So you were lucky enough to ride it out at home.
No, I wasn't. And yes, thank you very much for allowing me to participate and work with you on this presentation. I appreciate it.
Yeah, it was great.